I'm Professor Rad, and this is Precalc video 222, graphing exponential functions. So in our last video, we talked about several properties of exponential functions, and I have them listed kind of in an abbreviated form here over on the sideboard. These properties are going to help us to check our work as we graph, or they're even going to help us graph the functions. In particular, we have a y-intercept of 0, 1, and we have these 2 points, 1a and -1, 1 over a. And those points, those 3 points together, will give us some good points to graph our functions. So let's just jump into it. So for this example, we're going to graph 3 exponential functions. We've got 3 to the x, 1/3 to the x, and 3 to the x plus 1 minus 5. So let's start out simple. Let's start out with y equals 3 to the x. So we know it's going to have a y-intercept of 0, 1 because it's of the form y equals a to the x. So we know its y-intercept will be here at 0, 1. Then we know it goes through the point 1, 3 because our base is 3. And it's going to go through the point -1, 1/3. So I'm going to plot the point 1, 3. And then -1, 1/3. So it's a little bit trickier. So dividing this interval into thirds, about here. Now, these are enough points to get us to graph, but I'm going to go one step further. I'm going to use 2. So 3 squared is 9. So I'm going to graph the point 2, 9 as well. So we can see how very truly quickly exponential functions are going to grow. So these functions are smooth and continuous. So I'm going to connect the points in a smooth and continuous manner. And our base of 3 is bigger than 1. So that means we're going to have a horizontal asymptote at 0 as we go to -infinity. So I'm not going to cross that x-axis. I'm just going to get closer to it. So in fact, let me graph that asymptote with the dotted line so we can really affirm that it's there. All right, so let's try graphing g of x. So we'll call this one f of x. If you want to practice graphing an exponential function, then you can pause the video here and try graphing g of x on your own. And we'll see if we get the same thing. But if you want to walk through it because you need another example, we can do that together too. So for g of x, which is 1/3 to the x power, we're in the same situation where we have something of a to the x. So that means our y-intercept is still 0, 1. So we go through the point 0, 1. And we're going to go through the points 1a. So in this case, a is 1/3. So we go through the point 1, 1/3. And we go through the point -1, 1 over a. So a in this case is 1/3. And if I have 1 over 1/3, that's the same as 3. So we have the point -1, 3. And again, this is sufficient for us to draw our curve, but we can find another point by substituting in -2. So if I substitute in -2, I'm going to get 1/3 to the -2, which is 1 over, well, that'll be 3 squared, which is 9. So we have the point -2, 9. So looks like we are connecting upwards going this way. And that confirms this property here that said if a is less than 1, 1/3 is less than 1, we're a decreasing function. So as we move from left to right, this function is indeed decreasing. And a is less than 1. So we're going to be approaching 0 as x goes to +infinity. So x is going to be approaching 0 as we move to the right now instead of to the left. So again, let's do a quick sketch of that asymptote as well. So this is our function, g of x. Now, if we step back and look at these two functions before we jump to this third one, if we look at what's going on with these two, they look like they're basically the same function. They've just been reflected over the y-axis. So if we think about our transformations, a horizontal reflection like that would be having a negative x, right? A negative on the inside. So if I take 3 to the x, and I replace that x with a negative x, then I can think of that as 3 to the negative 1 to the x power, and 3 to the negative 1 is 1/3 to the x power. So actually, we're getting exactly what a transformation is telling us we should get. So another way we could have graphed g of x, if we wanted to, would have been using transformations on functions. But I think it's just easier to find these 3 points and then just plot accordingly. So now let's take a look at this third function, h of x. H of x is definitely a transformation on y equals 3 to the x. So we can see that we have 2 shifts happening on this one. We're going to shift to the left by 1 since we have a +1. And excuse me, we're going to shift down by 5 because of this -5. So we're going to start out with this as our base function and transform it to graph h of x. So when we go to do this, I like to transform that asymptote first so that I don't forget about it, and it helps guide me where I'm plotting my points. So the horizontal transformations on the asymptote are not going to have any impact, right? Because whether I shift this left or right, or whether I stretch that horizontal line horizontally, it's not going to do anything. However, the vertical transformations will have an impact on it. In particular, we're shifting this entire function down 5. So that means this asymptote is also going to get shifted down 5. So I'm going to start out by plotting my horizontal asymptote at -5. Then I can transform my other points accordingly. So I'm going left 1 and down 5. So I'm going to start out with the y-intercept. It was at 0, 1. So that's where we're starting. We're going left 1 and down 5. So 1, 2, 3, 4, 5. So it looks like I'm at -1, -4. This point that was at 1, 3, we're at 1, 3. We're going to go left 1 and down 5. 5. And then, oh gosh, this point was at 2, 9. So if I move it left 1, I'm at 1, 9. And down 5, I'm at 1, 4. And then this point here that was at -1, 1/3. I'm going to go left 1 and down 5. So 1, 2, 3, 4, 5. So I'm going to be just above there. And now we can connect our points along with our function. And there we go. This is our function h of x. Now, absolutely, you could pick values to substitute into that function and graph. However, when you use transformations, you have a good idea of what your domain and range will be based off of those transformations. You also know where some nice points are. So like in this case, because my base was a whole number, if I pick points randomly, I'm probably going to get a nice value. But if my base was 1/3, I might get some really weird looking points that are challenging to graph. So if I know what that function looks like, then I can graph it using transformations pretty smoothly. All right, so that's it for graphing these 3 functions. But before we end this video, I want us to think about this last property here, that these functions are 1-to-1. That means that these functions have an inverse. So let's just take a quick moment and look at the inverse of this red function here, this f of x. So let's clear some space and graph its inverse. Alrighty, So remember, to graph the inverse of a function, you're going to switch the x and y values. So something that I was noticing on the first test this semester that I'm making this video was that some folks wanted to find f of negative x to find an inverse. That's not what we're doing. So an inverse is not a horizontal reflection, right? That's what we found here. An inverse is when you switch the x and y values. So when we go to graph the inverse of f of x, I'm going to start by switching my x and y axes, because notice these axes are very different. So now, instead of my horizontal axis going from -4 to 4, that's going to be my vertical axis. And instead of my vertical axis going from 0 to 10, that's going to be my horizontal axis. So I'm going to switch the axes as well as the coordinates of my points. So 2, 4, 2, 4, -2, and -4. Now, let's also graph the asymptote while we're switching the x and y values. So in this case, we had a horizontal asymptote, which has the form y equals 0. So now we're going to have a vertical asymptote for the inverse of x equals 0. So we're going to sketch that vertical asymptote. Now we can switch the coordinates of each point. So this point 0, 1 is going to become the point 1, 0. This point 1, 3 will become 3, 1. 2, 9 becomes 9, 2. And -1, 1/3 is going to become 1/3, -1. And we can connect these points accordingly. So this is going to be the graph of our inverse function of x, f inverse of x. Now, if you're thinking about your common functions page that we did way back at the beginning, this looks like our logarithmic functions. That's because exponential functions and logarithmic functions are inverses of each other. So this is actually the same as the graph of y equals log base 3 of x. So in the next several videos, we're going to be talking about logarithmic functions, because the inverse gives us a way to undo exponential, the base of an exponential function to solve equations. So we're going to start delving into some of the properties of logarithmic functions in the next video. And we want to hold on to this graph and this relationship that exponential functions and logarithmic functions are inverses. So when you get stuck with logarithms, just think back, think of the exponential expression instead, and then switch your x's and y's. So that's going to be it for this video. I hope it helped you to graph some exponential functions, and I look forward to the world of logarithms to come in the future set of videos. So hope you have a fantastic day, and I'll see you next time. Bye for now.